Welcome to the next video in the crystal structure refinement series. We're going to look into data processing now using CrysAlisPro. So I have here downloaded raw dataset. You can get this dataset from a link that should be somewhere under the video. It's one of the datasets that I recorded. It's a very easy porphyrin molecule. There is no disorder, nothing fancy. Really just to see how to work with this software, and we'll process it now using CrysAlisPro, and later in another video we will solve, refine and finalize this crystal structure. Okay, so if we double click on the par file, on the parameter file in this raw data folder, CrysAlisPro should open. CrysAlisPro can be downloaded for free if you register on Rigaku forum website. You can download it for free without any problem. Okay, so first here you can see some reflections. They are frames, diffraction images, so if you scroll you can go through them, but the thing I don't like are the default settings, so I'm going to try to change it a little bit. So I'm going to change the appearance to X-ray film. Looks more like that. I prefer it this way. And we're also going to add resolution rings. And now, at least for me, it looks much better. We can play the whole data collection movie, so you can see that the reflections are pretty strong and they reach more than 0.8 angstrom resolution. So it's a pretty good data set. Let's have a look at the lattice wizard. We can do peak hunting now to basically search for peaks, for reflections. And I usually do it using multiple processes to make it faster. So I will now run it. In the meantime, I will stop, and when it's done, because it will take a few minutes, when it's done, I will resume recording. Okay, it found all the peaks. Now if we click unit cell finding, it will propose us a unit cell. It's a primitive unit cell, triclinic. Here are the parameters of the unit cell. Let's reindex it. Okay. So a useful thing is to go to Lattice Wizard. We can open Ewald Explorer to look at the Ewald sphere. We can, by clicking here, we can look at the Ewald sphere at different projections, at different orientations. For some reasons I have problems clicking here, probably because of the movie recording software has an icon somewhere there, but oh, now it should work. Yeah, and we can also rotate it like this. If you want to do something fancy, you can look at it from a bit different views, but it's not that useful, but definitely looks kinda fancy. Okay, so here we can see that it indexed almost 5,136 reflections, and only 7 of them are wrong, which means that it's a really nice, very single crystal. Okay, so let's start data processing now. So we go to start stop. I usually go for data reduction with options. So we're not using any filter, it's p-lattice. Okay, next. Here we can, for example, select runs. So if we don't want some runs to be included in the whole process, we can get rid of them, but we're using all of them. There are no problems. There are some things that we can change in the special parameters, but in this case we're not going to do anything. It's quite a standard data set. A very useful thing to do, especially if you have, well, in situations when your diffraction doesn't reach 0.8 angstrom, but you still recorded it, you can trim the data by using resolution limits. So for example, if you have only diffraction up to 1.1 angstrom, you can set it here, so it could do all the integration, everything only up to 1.1 angstrom. so it could forget about anything else about them, basically non-existing data beyond, to not do any scaling and things like that for the noise that you have beyond. But our data set is basically perfect, so okay, we're not changing anything here. I will click clear data from previous run because previously I was doing some data processing, so to make sure that everything's fresh, I will just clear all of it. Next. We have two options for integration background. So we have average background, and as it says, it's good for stable and low background fast. The smart option is for a bit weaker data with higher background. My data are usually quite weak, so I usually go for the smart one, but well, let's do the average one. Next. Manual space group determination, so we could see all possible options rather than only relying on the software, and we can do finish now. So it will do now all the integration stuff. So it will take a couple of minutes, so I'm going to stop the video now and again start recording when it's done. Okay, it has just finished, so we see this window for space group determination. So we do apply. It's suggesting us that we have p-type cell, yeah, triclinic, yeah, again, yeah, it looks like centrosymmetric structure, yes, for example here, yeah, centrosymmetric, so it's p bar 1, centrosymmetric, apply. Okay, I think that's probably even a correct formula. So with that z, our density is 1.237, mu is 1, so absorption is not large. There's only one zinc ion per large organic part, so it's not that surprising. The density in general for this, molecular, let's say, compounds without million of heavy atoms inside should be between like 1 and, I don't know, 1.4, 1.5. So it's all reasonable. We can do finish now. So it's doing some calculations. For now, it's telling us that so we have some data to parameter ratio, average redundancy, and we have rint. Our rint is 2.8%, so it's pretty good. Okay, the next thing we want to do is to go here, inspect data reduction results. And there are some things we can do. For example, if you go to, we can have a look, for example, here, but we can go to reduction graphs, and something that is worth to look at is, for example, rint. So you can see that there are some frames where rint got very high for some reason. So then we later, when it comes to final processing of the data, we'll be able to cut these frames. So let's just remember for now that these very weird high rint frames are, let's say, 0.1. We'll cut somewhere there, 0.1. But okay. We can also click here to look at the crystal movie. And we can see a movie of a crystal. If that was a compound that has very high absorption coefficient, that's also a window where we can define phases of a crystal to a different type of absorption correction. But we're going to use multi-scan absorption correction, so we don't need to do that. But anyway, here we can see, for example, measure the distances that we can then insert the CIF file and say what were the dimensions of a crystal, right? So pretty useful thing. Let me close that. Okay, so now to finish everything, we go to refinalize. So export, it's best if you go from the bottom to the top. So export options. We want a file which will include HKL. We can change the output name. As you can see, I did some processings before, so let's call it tut, like tutorial. Start new branch, okay. And filters and limits. That's the thing that I said about removing some of the frames. So we'll do it manually. Filters, add, it was rint filter. Yeah. And we want to cut it at 0.1. Let's say 0.12, why not? Because these frames, we don't want them, okay. Completeness 0.8 angstrom. If we set before some resolution limits, for example, if we were processing the data only up to 1.1 angstrom, because our sample diffracts like this, we can also change it here to 1.1 as a resolution limit. And again, let's do interactive space group determination again. If we leave these options like here, we'll just do multi-scan absorption correction. So that's reasonable for this type of compound. Okay. So it's now processing, blah, 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 blah. Come on, come on, come on. Okay, and now GRAL opened. That's the thing for space group determination. So we already know how it should be, but yeah, primitive. Apply, triclinic P, yes, centrosymmetric, yes, it's P bar 1, centrosymmetric. The formula is probably correct. If the formula is not exactly correct at this point, it doesn't really matter a lot because we're doing multi-scan absorption correction. But if you were doing these phase, absorption corrections that are based on indexing phases, then your formula should be good. I mean, it probably won't matter if one carbon atom would be off, but if you have, for example, I don't know, 5 heavy atoms and instead you will put there 7 heavy atoms, that would probably matter a lot. But as I say, for the absorption correction that we're going to employ for multi-scan, we don't really need to care about formula, but the formula is at least more or less correct. I think it's probably even perfectly correct. So finish. And it's done. So final rint was, well, as before, 0.028, 2.8%. So our process data, where can we find it? We go to the folder struct, and it's here. Everything's in that folder. So our ints file, input file for the refinement, HKL file with all the intensities information, and there's also CIF-OD file. The CIF-OD file contains both HKL, if we clicked that during processing that we did to contain HKL, but it also contains all the details about the diffractometer, and it will be necessary to finalize the structure later in OLX2. So that's it about this video, and in the next video we'll have a look at the solving the structure, refinement, and finalization. Thank you very much. I hope that was useful.